Assalamu alaikum. Hello everybody. This is a video about differentiable functions or non-differentiable functions. The first question or exercise, let f of x be equal to exponential x, 1x is less than or equal to 0, x plus cosine x, 1x is greater than 0. Does f belongs to C1 of R and does f belongs to C2 of R? We mean by C1 of R that f is differentiable and its derivative is continuous. And we mean by f belongs to C2 of R, f is twice differentiable and the second derivative is continuous. The second exercise, give an example of a function f from R into R which is differentiable just only at x equal to 1. Let us start by the first question. So f, domain of definition of f is equal to R if x is different of 0, f is composed as addition and just addition, f is differentiable as elementary functions because if x is less than or equal to 0, f of x is equal to exponential x, which is C infinity, which is differentiable once and twice and more. And if x is strictly greater than 0, f of x is equal to x plus cosine x, which is differentiable. Let us focus on x equal to 0. When x goes to 0, from this side it is equal to 1 and from this side it is equal to 1. So it is continuous. We can talk about the differentiability at x equal to 0. F prime is equal to exponential x when x is strictly less than 0. It is equal to when x equal to 0. We will find it later. And is equal to 1 minus sine x when x is greater than 0. What we can write here? If we can find the derivative, we will write here f prime of 0 if we can find it. F prime of 0, this can be equal to the limit of f of x minus f of 0 over x minus 0. When x goes to 0, we have two sides from the left and from the right. If the two limits are equal, then we can say that they are equal to f prime of 0. From the left, the limit of f of x minus f of 0 over x minus 0 when x goes to 0 from the left. From the left side, we will use this expression. This is equal to the limit when x goes to 0 from the left, exponential x minus f of 0 exponential 0, so 1 over x, and this is equal. We can use three methods here at least to define the limit. We can use the definition of the derivative at 0 of exponential x, so this is the derivative applied at x equal to 0. We can use L'Hopital rule. We can do derivative both of them since we have 0 over 0, and we can use Taylor expansion to find that it is equal to 1. From the right side, we have f of x minus f of 0 divided by x minus 0 when x goes to 0 from the right. This is equal from the right, so it's equal to x plus cosine x minus exponential 0, which is 1 over x. Here once again we can use Taylor expansion development. We can use rule theorem. We can L'Hopital rule. We can divide, and from a side we take x over x, which is equal to 1, and from the other side we take cosine x minus 1 over x, and cosine x minus 1 over it is the derivative of cosine at the point 0, so we take the derivative, which is equal to minus sine applied at x equal to 0, so this is equal to 1. I think that we have here at least three ways, three different ways. So from the left and from the right they are equal, then we can write that it is equal to 1. To say that f is differentiable, yes, we can say this. F is differentiable. Can we say that f belongs to C1 of R? Not yet. It is differentiable, and the function, which is the derivative, it is continuous. Why it is continuous? Because when x goes to 0 from the left, we find 1, and when x goes to 0 from the right, we find 1. So the limit of f of x is equal to f of 0. The limit of f prime of x when x goes to 0 is equal to f prime of 0. This permits us to say that f belongs to C1 of R. How about the second question? Does f belongs to C2 of R? First, does f prime admits another derivative? We will see. F second at 0, f is there as an elementary function. It is actually infinitely differentiable, so it is of the class C infini if x is different of 0. So the second derivative exists, the second derivative exists if x is less than 0 and if x is greater than 0. But the question, we are arguing with x equal to 0. F second equal to 0. If this exists, so it is equal to the limit of f prime of x minus f prime of 0 over x minus 0 when x goes to 0, from the left and from the right. Let us start by the left. So this is equal to the limit when x goes to 0 from the left. From the left, the derivative, we are here, so we are here exponential x minus 1 over x, and the same technique, it gives us 1. The limit of f prime of x minus f prime of 0 over x minus 0 when x goes to 0 from the right. This is equal to the limit of 1 minus sine x minus f prime of 0 minus 1 over x when x goes to 0 from the right, and this is equal to minus 1. We cancel 1 with minus 1, and we get minus sine x over x, which is equal to minus 1. Since the two limits are different, so f prime doesn't accept derivative at x equal to 0. This means that f isn't twice differentiable on R, but it is twice and more nth differentiable on R star. But on R, it is not differentiable at x equal to 0. So the second question is no, it is not C2 of class C2. The second question, can we define, can we give an example of a function f from R into R which is differentiable only at x equal to 1? Actually, yes, we can propose this one. F of x equal to x minus 1 square if x is rational, if x belongs to Q, and equal to 0 if x belongs to Q complement. We suppose that x is different of 1 for x0, which is different of 1. This function, it is not continuous. So f isn't continuous. We saw this before, but anyway, we can repeat it quickly. Let x0 different of 1. In this case, we have two cases. x0 different of 1. The first case and the second case is different of 1, but x0 belongs to Q, and different of 1 and x0 belongs to Q complement. We start by the first case. So we suppose that x0 equal any rational number, but is different of 1. In this case, what we have? We have f of x0, this is equal to x0 minus 1 squared. And since for a rational number we can find a sequence from the irrational numbers that it converges to x0, since Q complement is equal to R. This implies that we can find a sequence R and from Q complement such that R and converge to x0 when n goes to plus infinity. In this case, from a side, what we have? From a side, we have f of R n. This is equal to 0 because Rn is in Q complement, irrational. And from the other side, what we have? We have f of x0. This is equal to x0 minus 1 squared. x0 is different of 1, so this is different of 0, but this is equal to 0, when n goes to plus infinity, so we have 0, and at the limit we have 0 equal to x0 minus 1 squared. This is a contradiction with the fact that x0 is different of 1. So if x0 is a rational number, the function f, it is not a rational number which is different of 1, so f is not continuous. We do the same technique here, we can use the same technique here to show that if x0 is not is in Q complement, irrational, then the same technique, just in this case what we will get from this side it will be equal to 0, and from this side we get a sequence from Q which converges to x0 which is in Q complement, and we have actually the same thing, the same contradiction. A function which is not continuous at a point, it cannot be differentiable. So f cannot be differentiable at all the points except x0 equal to 1. For all x0 from R such that x0 is different of 1, f isn't continuous. So f isn't continuous, so it cannot be differentiable. F is differentiable at x0 equal to 1. It is continuous. We can have a proof by using the characterization for any epsilon greater than 0. There exists delta. This delta is equal or less, is less than or equal the square root of epsilon, such that f of x minus f of 0 less than epsilon for all x, such that x minus 1 is less than delta. We use the characterization. I am sure that you understand what I am meaning here. So it is continuous, and more than it is differentiable. Why it is differentiable? It is differentiable, but because if we consider the limit of f of x minus f of 1 over x minus 0, the limit 1x goes to 0. This is equal to the limit of f of x, I mean x minus 1 square minus 0 over x minus 1. 1x goes to 0, to 1, sorry. 1 here, 1, sorry, once again. This is equal to the limit of x minus 1. 1x goes to 1, and we use the same technique that we use here to prove that this is equal to 0. The same technique we're using the characterization. So this function is actually a differentiable function just at x0 equal to 1, and not one more other points. So it is actually a very special function. I will check the time of this video. Is actually approximately 20 minutes. I can add 5 minutes. Let f be a function. Let f be a function defined from R into R, which is differentiable at a point x0 from R. What we can say in the absolute value of f, is it differentiable? Is it differentiable at x0, the same point? We have two cases. If f of x0 is equal to 0, the answer is yes. The answer is yes. Why the answer is yes? Yes, this is the question. So, but if the is different of 0, the answer is not conclusive. The answer is not conclusive, means that it depends on the cases. Now, I think that no. Sorry, it cannot be true like this. This is the case for the teachers, but they doesn't prepare the exercise. I think that if f of x0 is different of 0, if f of x0 different of 0, the answer is yes. Why? Because in this case, suppose that f of x is different of 0. Don't forget that f is differentiable. This is an hypothesis. If it is differentiable, this means that f is continuous. If it is continuous, f continuous and f of x0 different of 0, this implies that there exists a neighbor of x0 such that for all x in this neighbor, f of x0 is different of 0. Okay. The absolute value of f of x, it can be equal to f of x0 or minus f of x0. Let us take the first case. And for the second case, it will be the same technique. Let us suppose that it is positive. So in this case, what we will get f of x0, which is equal to f to x0. And here f is differentiable, and we have a neighbor on which f of x is greater than 0. In this case, what we can say, simply that f is differentiable, that the absolute value of f of x is differentiable. Why it is differentiable? Because f of x0 is differentiable and it is greater than 0. So in this case, f of x, which is greater than 0, is differentiable. If it is less than 0, minus f of x0 is differentiable. We can find the same technique. It's differentiable. Since f is differentiable, so minus f is differentiable. The second case, if f of x equal to 0, I think here it depends on the cases. This is here, it is not conclusive, so it depends on the cases. We take the first case, when known one, f of x equal to absolute value of x. So f of x, which is equal to x, is differentiable. This function is differentiable at x equals 0. So this function is differentiable at x0 equals 0. But this one isn't isn't differentiable at x0 equal to 0. We know this. We have -1 and from the left and 1 from the right. Otherwise, f of x, which is equal, for example, x, the absolute value of x, this verifies at 0. It verifies f of 0 equal to 0. But this function is differentiable. If we take, for example, f of x equal to x power 3, it verifies that f of 0 equal to 0, but this function is differentiable at x equal 0. If we take f of x equal to x, the absolute value of sine x, this function verify f of 0, and this function is differentiable at x equal to 0. And we can provide more examples like this. Just we can retain that the differentiability depends on the fact that f of x0 is equal to 0, so we cannot decide previously if it is differentiable or not, but if it is different of 0, so it is differentiable for sure. You will find more video next time, inshallah. Thank you for watching this video, and see you next time by the mean of video for sure.